Hello, everyone, and welcome to another mini sky tonight. So last time I covered over the first part of black holes, basically introducing some of the main concept of black holes, what they are, how they're formed, and why they're dangerous. So if you want to check out that video before diving into the history of our discovery of black holes, I'll leave a link up here so you can check that video out first before diving into here. So today I wanted to discuss about our history in discovering black holes, because black holes have existed since close to the beginning of our universe, but it was our understanding theoretically and finding evidence for it wasn't until much later in our history. And as we got to explore our cosmos a little better, we got to understand these unique things in space. So let's dive into the history of how we discovered black holes and what we know today. So believe it or not, it starts in the 1700s. In 1783, British scientist John Michell predicted that objects of extreme mass could be so massive that light couldn't escape. This comes from the concept of Newton, to where he was the first to understand that an object, if it was given enough speed, could go into orbit around another object. It was Newton who gave us the idea that things could be put into orbit around another, like how our moon is in orbit around the Earth. It's going fast enough to where Earth's gravity can't catch it. So John Michell took it a step further. Could it be possible that an object is so massive that no matter how much energy you give an object, even if you put it close to the speed of light, it could not escape? So it was a unique theory and a unique hypothesis to basically muddle around. And he had in his paper, some evidence for the possibility of an object to exist, but there was no evidence or proof. But it was later in 1796 that Pierre-Simon Laplace proposed that maybe it's not a physical object like a planet per se, but what if it's a star? So Laplace understood that possibly in order to get something of this mass, maybe you need something big as our star, if not even bigger than our star, to where that dark star, in Laplace's theory, that instead of radiating out light, heat, and energy, that it's so massive that that light that would normally radiate outward would go back in on itself, creating a dark star. And even Laplace had a bunch of equations to prove the existence of this supposed dark star. But again, there's no observational evidence of such, because as one critic put it in his paper, he said, okay, if you have a dark star, how would you see it? And it's got a point. I mean, black holes, even for what we know today, you can't visibly see them. So that means it took some more evidence and some more understanding of how our universe works before we could really tackle this problem. And it was in the 1900s where a brilliant scientist, Albert Einstein, came up with his two theories of special relativity and general relativity. These two theories basically revolutionized our understanding of how our universe worked. Back in the day, we depended upon Isaac Newton's forms of gravity as well as his laws of motion. It was Einstein who basically took Newton's laws and expanded upon it. And it opened up the door for new possibilities of understanding how our universe worked. And it was revolutionary at the time. In fact, just to show you how amazing these two theories are, Time magazine, who names like the person of the year, they named him person of the century because his understanding and how it expanded our universe so much was so profound. So let's discuss these two theories and why it helped us better understand black holes. So first off, special relativity. So basically, the idea of special relativity is that there's a concept in physics of conservation of mass, conservation of motion, conservation of energy, that you don't lose something. it basically transfers from one to another. Einstein took it a step further and said, okay, not only can you have motion transfer to motion or motion transfer to energy, but what if you could transfer mass into energy? Like taking some type of material and making it into energy, not by chemical reaction or anything, but actually making energy become mass or mass becoming energy, and so on. And this revolutionized our understanding of how stars work in the process known as nuclear fusion, where you literally take two hydrogen atoms, ram them together to produce helium atoms, plus light, heat, energy, and other particles. So the fact that you can take mass, ram it together to produce energy was profound. And of course, it's often embodied in the famous equation known as E equals mc squared. That basically you can have energy and mass inter-exchange between each other. As well as it helped us revolutionize our understanding of nuclear fission, basically how nuclear power plants work. Like you take a uranium atom and you split it, and you can produce energy from that split. So from the fact that you take a mass, break it apart to produce energy. So the idea that you can have energy being transferred into mass and mass being transferred into energy helped us revolutionize our understanding not only of stars, but how the subatomic particles work, as well as atomic particles. The next thing about special relativity is that the speed of light is the same no matter what speed the observer travels. So if you have a person who's standing still versus a person who's on a bullet train, the speed of light would always be the same and it would appear faster than they are no matter what. So the speed of light wouldn't look like it's starting to slow down even though you're on a bullet train. So kind of think of it this way. You know how sometimes when you're on the highway and you're passing up a person to your right because they're going slower than you are, and it looks like they're going backwards. Some people speculated, okay, if you get closer and closer to the speed of light, it'll look like the light is slowly starting to go backwards. And this kind of started to give the concept of like time travel and things of that nature. But according to Einstein, he said, since light is so fast, and that in order, from his equation, that in order to get to the speed of light, you have to have mass that's close to infinite, you're unable to make the trip because you have to have so much energy to be able to go at the speed of light. So you would never be able to go faster than the speed of light. You can get close to it, but never at exactly speed of light. And no matter if you're getting as close as possible to the speed of light will always be faster, and it will look like it's going at the same speed. So this revolutionized our understanding of how light works, how energy works, and as well as how stars and our subatomic particles work. So the next step is general relativity. So this theory expanded upon the universe, and it starts with a concept known as space-time. Everything occupies its own space in its own time. So imagine kind of like a cube box, if you will. It's sitting in its own place in its own time, but time keeps moving forward. So even though it's sitting still, it's still occupying that one place at that one time. And even though time keeps moving forward by seconds, it's still in that XYZ. So Einstein decided to kind of interweave those two concepts rather than having space like XYZ and time as two separate entities. He mixed them together to give us the concept known as space-time, where everything that occupies its own space and its own time, and that gravity, any type of force, can alter the fabric of space and time. So when an object is in space, it can distort space and time, allow it to bend around. So that way empty space can't inhibit the same space as a certain object in a certain time. It basically makes way for it. And the more massive the object it is, the more it distorts space and time. So we've actually seen this where if you have like a galaxy, which is incredibly massive, it can distort space-time so much that anything behind it will look like it's appearing, because light travels along space-time in a straight path. But if that space-time is distorted, it will follow along with the distortion, basically allowing light to bend. We call this gravitational lensing, where basically gravity causes light to curve around whatever massive object it is. And in gravitational lensing, when we see it in pictures, it looks like we see like these weird distorted galaxies around a central object, or like mirror image of it. Another famous example of this that we discovered much, much later is called Einstein's cross. If you want to check it out, just Google Einstein's cross, and it's basically the same galaxy mirrored several times. But of course, back in this time, in 1909, nobody had proof of this. Nobody could say, okay, these are great theories, but how do we prove them? Well, a group of scientists got together and realized that in 1919, a solar eclipse would occur. And according to Einstein's theory, the sun has enough mass that it could distort light enough. And in 1919, with a solar eclipse, what they could do, and what they ultimately did, is they took two telescopes, one in South America and one in Africa, and they put solar filters on these telescopes and took pictures of the solar eclipse. But more importantly, they were focusing on the stars that were around the sun that was being blocked out. Because as the sun is being blocked out, the stars would appear. And as the stars appeared, they took photographs of those stars. And they compared that photograph of the stars around the sun to another photograph they took much earlier in the year of the same area of the sky at night. So you have the constellations and the stars at night, and they compared it to that same area, which should be the same during the solar eclipse. And they noticed that the stars around the sun were out of place. Stars that should have been behind the sun were now barely visible at the bottom of the sun. So it proved that the sun had enough gravity to bend starlight. So this proved Einstein's theory of general relativity, that massive objects can bend light because it goes around in space-time. So this revolutionized a lot of different things, and it opened up the door for other scientists to be able to expand upon this idea. In fact, in 1916, Schwarzschild published a solution to Einstein's general relativity near singularities. So basically objects that were so massive that basically it looked like light could either be distorted so much that you can't really detect it, or even so that light is so distorted that it goes down into the singularity. In 1939, Oppenheimer and Schneider described how we can get black holes. So they were studying a bunch of stars and they noticed certain patterns, and they thought, basically it would be like taking pictures of individual people at different stages in their life and then kind of created a timeline for the human evolution. Like basically starting from a baby going to an older person in their hundreds and every step in between, and basically could see the natural transition. They kind of did that with a group of stars where they noticed certain transitions in their life cycle, and that the possibility of, what if the star is so massive that the core collapsed down into a black hole? And they were the first to propose that idea. In 1963, Schmidt discovered what is known as the first quasar, a quasi-stellar light source. This was a light source that when they were able to calculate the distance to it, it was exceptionally far away, but it was an incredibly bright source. And it had so much energy that they had to think that, okay, in order for this object to have so much energy, it has to have a powerful source to produce this energy inside of it. And the only thing that they could think of was a black hole. Now, before this time, the term black hole was tossed around fluently in the astronomical community, but it was never really penned per se. It was, they called them their objects of interest, and or they called it like X-ray sources or gamma ray sources or radio sources, etc. But they never really put the term black hole into their publications, because it was, they sometimes use singularities, but they never really used the term black hole. It wasn't until 1964 that the first paper published used the term black hole. They were bold enough to say, you know what, we're going to use the term because that's what these objects are starting to look like. And they put black hole. So from this first publication in 1964, that term bloomed outward. And of course, the media took hold of it and it went crazy that there are these big holes that are black out in space. And in 1972, the first discovery of a black hole. Astronomers discovered Cygnus X1, which was a known area for bright X-ray sources coming from it. But there was nothing there. They didn't see any stars that could produce that same energy in that vicinity. So what was it? They didn't know. So they predicted that possibly this could be a black hole, that it's engulfing material and producing X-rays. And of course, in 1974, Ballack and Brown discovered Sagittarius A star, a huge radio source in the center of our galaxy. They noticed a couple of other radio sources, and they were able to pinpoint what these objects were for the most part. But this particular one was in an area that seemed to be kind of void of stuff. And they weren't sure why, so they dubbed it Sagittarius A star, because it was a bright radio source that they couldn't pinpoint an exact star to it. And that same year, Stephen Hawking published his concept of known as Hawking radiation, because the concept of black holes getting bigger was understandable, that it basically was these black holes were gaining material to become bigger and bigger, and or they would collide with other black holes, possibly. But they noticed that some black holes, what causes them to basically dissipate, or do they dissipate at all? And it was Hawking who basically came up with the idea that yes, they can indeed dissipate out, as well as why we see some of these X-ray and radio sources coming from black holes. It was from Hawking radiation. Basically, and I kind of can explain Hawking radiation in the next slide. It's a unique process to where the creation of material causes that material to be radiated outward. Next step, in 1978, they noticed that the motion of stars in a galaxy known as M87 hint that a black hole exists in the center of it. They noticed that basically stars would go around the galaxy at such a certain speed that, especially near the center of it, that hinted that possibly there could be something gravitationally pulling towards it. And in 1992, Genzel observed the same thing with stars in our galactic center. And you kind of can see it in this little picture right here. This is where the galactic center is. And all these individual stars seem to be orbiting this one particular point and not touching that one particular point. And that point was not a star itself. It's like looking at our solar system, but all of a sudden the sun disappeared. So instead of the planets orbiting a star that has a bunch of gravitational pull on it, it's orbiting something unknown right there that we can't see. And he did this over the course of 10 years. And looking at the pictures of these orbits of stars over the course of 10 years, they noticed that over time, they calculated the periods of the stars, and given the rough mass of the stars, they said, okay, given the rough mass of these stars and how fast they're going around this object has to be incredibly massive. So this was good hard evidence towards a black hole. All right, now to get into Hawking radiation. Around black holes, there's strong gravitational fields around the black hole. And sometimes these black holes with these strong gravitational fields, can cause pair production, basically a particle and an antiparticle to be produced. Now, if, say, for example, one of these members falls into the black hole because it gets too close, that other member can still escape. So therefore, you have a antiparticle that's consumed, but the particle still exists. So you created a particle out of nowhere, and it comes out in form of radiation. So basically, the amount of mass lost because of this pairing is basically caused it to be radiated outward. Because as that antiparticle goes into the black hole, it pairs with another particle and then disintegrates, and then you still have this other particle that basically created mass. So you're taking mass away from the black hole. So keep in mind, this basically allows for like certain size black holes to disintegrate over very short times. But for many bigger black holes, this Hawking radiation takes much longer. But it showed why it was deadly to get near a black hole, because you have all this material being radiated outward from the black hole itself. All right, now into what we kind of know today. In 2008, the Event Horizon Telescope released and confirms a black hole-like object rests in the center of our Milky Way galaxy. They were able to take gravitational lensing, as well as they were able to find out different evidence to confirm that indeed there is a black hole in the center of our galaxy. And in 2012, they proposed a potential firewall around black holes. This is a new kind of concept. So rather than having to worry about spaghettification, they thought, well, with Hawking radiation and as materials being put in through the black hole, that you could possibly burn up. Yeah, so not very friendly of a place to visit. And in 2016, the Ligo Observatory, which is a picture up above, is a series of different radio dishes that are able to detect gravitational waves around black holes. And they were able to detect two black holes colliding. And they saw the ripples of these two black holes colliding. So that helped us prove that how supermassive black holes came into existence. It's basically a bunch of little black holes coming together and ramming together and creating these huge black holes. And from there, they were able to propose why our black holes in the center of our galaxy are so big. Because near the center of our galaxy is a bunch of big blue stars. And those big blue stars can sometimes develop into black holes. So you have all these black holes near the center of our galaxy, and sometimes they can interact with one another. And if they do, we get the supermassive black holes. And of course, in 2019, we get the first picture of a black hole in M87. We were able to have enough technological advancement to where we could see something engulf around the black hole completely, to where we see the image of the black hole. And this was a profound step, because we're able to see partial images of black holes or hinted at black holes in different light. But this was the first actual picture of a black hole where we noticed something, and as you can see in the bottom right, something that was being engulfed around it, and we were able to get an idea, okay, it's engulfing around something in the center there. And of course, scientists and astronomers are still learning more as the years go by. So this is the history of us discovering black holes and what we know so far. So as you can see, this is a unique area of study. And to quote a famous astrophysicist, he said, if you take all the rules of what you've learned in your physics textbook and you throw it out the window because it doesn't apply to a black hole. So we're even still trying to understand the basic concepts of a black hole and how it technically work. So if you have any questions or comments, leave it down in the comments below. If you have a topic you would love for me to cover over, leave it down in the comments as well. And until next time, stay safe, stay healthy, and as always, never stop learning.